Hi, in this video, we will solve the partial differential equation, which is the PDE, by using the numerical method. So in general, PDE is the equation that has two or more independent variables. So we have one equation here, and from this equation, you can find two derivatives. If let's say these two derivatives at the bottom, which is the denominator, we found two symbols, which is x and y. In this case, x and y are the independent variables. And for the numerator, which is the u, this is known as the dependent variable. So normally, we want to find u in terms of x and y function. So we can write the term, okay, the u function that we want to find is in terms of x and y. So by solving this PDE, we should be able to find the answer for this. In this case, let's say you want to find the temperature, okay, distribution over the x and y dimension. For example, you have a plate, okay, so let's say in this direction we have x direction and this is our y direction. So you want to know what is the temperature distribution on this plate. So we can find it using this PDE. In case we have only one independent variable, so let's say you only have one independent variable. So in this case, let's say we let this term to be 0. So we only have this derivative and we only have one independent variable, which is x. So normally we call this as ODE, ordinary differential equation. And what we want to solve is we want to find the u in terms of x only. So normally for ODE, we are using the symbol delta here, delta square u over delta x squared. So for this type of problem, we can use the midpoint method. Euler method or Runge-Kutta method to solve it. So these are the things that we have discussed earlier. Okay, we discussed basically the Euler is the first order, midpoint is the second order, and Runge-Kutta is the fourth order method that we have learned to solve the ODE. So in this week, we will further discuss how to solve the partial differential equation here if we have more than one independent variable. So in this case, you have x, y, or z. Okay, you have more than one independent variable. The delta u over delta y here is referred to the partial derivative of u with respect to the y. Okay, so previously we say, let's say our u is in terms of xy independent variable. So let the u to be the temperature distribution. So let's say we have a plate. Okay, so this is our x-axis and this is our y-axis. So any point here, okay, so let's say we want to find the temperature. So any point here, the temperature can be described by this function, u function here. So if we want to find the delta u over delta y, so we can use this equation. So this equation, you can see that the u is in terms of xy, and the delta y is the step function in terms of y-axis. So we have our delta y here. So this is our delta y. So let's say at this point, we can have the u x, okay, because it's the same axis for the x direction, and y-axis plus the delta y because it's on top, right? So USY is at the point that we want to calculate the delta U over delta Y. Right? So you can give the information here. So for example, at this point, the temperature is 50. So you can substitute here 50. And the point on top is let's say 60. Then you can substitute the temperature here to be 60. So delta Y here, okay, is the dimension between these 2 points. So for example, the delta Y, you choose it to be 1. Okay, so you have to substitute, okay, 1 here. The distance between these 2 points is 1. So of course, if let's say you choose the step size delta Y to be 1, the accuracy for delta U over delta Y will be low. Okay, and if you choose a smaller step size, 0.5 or 0.05 and so on, okay, let's say you choose much more closer to 0, okay, when delta Y much more closer to 0, the accuracy can be improved, and this can be approximate equal to the limit here. Similarly, to compute the delta U over delta X, okay, we need, okay, UXY, assume that the UXY point is here, which is 50 degrees Celsius. So for this one, you can see the dimension X plus with the step size delta X. So assume delta X is here, you select it to be 0.05, 0.05. So the point next to 50 here, okay, assume that you measure it, is around 45 degrees Celsius. So this will be your result here. So 45 minus 50, you get -5 divided by 0.05. This is the approximation result for delta U over delta X. Approximate symbol is like this. Okay, so we don't have the equal. Why? Because in actual, this limit cannot be achieved, right? We cannot get the delta X exactly equal to 0. So when this E exactly equal to 0, then this can be equal. But since this is approximate to 0, so we can only have approximation here. In this study, we will solve the second order and linear PDE. So this is the general form for it. So as you can see here, so the power is 2 for the derivative. So this is known as the second order PDE. And also the constant A, B, C, D are found here. So this is for the linear case. So we would solve something like this. So in this case, it's the third order, so we won't solve these kind of cases. And also, let's say in this case, you have U with power of 2. So in this case, it's non-linear, or you have some sign, U, etc. Or you have the constant here, C, okay, you multiply with U. So this is non-linear case also. So these are the cases that is out of scope. So A, B, C, D might be constant. It might be also in the function of X and Y. So if this is in X and Y, okay, it's still linear PDE. Unless you have U, okay, then it's non-linear. So then your mind, A, B, C, D, not only constant, it might be involving X and Y, which is the independent variable. So if you have this, then we have linear PDE. So based on the A, B, C function here, so if we're able to find it using this formula b squared b squared minus 4ac, if let's say is equal to 0, less than 0, or greater than 0, we can separate it into 3 cases: elliptic, parabolic, and hyperbolic. So once you compute the a, b, c, and substitute inside this formula, let's say you get it less than 0, which is negative value. This is known as elliptic PDE. So there's one example here. So for example, Laplace equation. So this is the Laplace equation, where based on this you have the a equal to 1, and here also 1, which is the c. So your c is equal to 1 as well, and b is 0. So by substituting inside this formula, you get this. So which is negative 4 less than 0. So by repeating the same procedure, so you have to arrange this into linear form. Let us switch to right hand side. This becomes negative. This becomes 0. So in this case, your a, based on this, it will be this term. So this is your a. How about your b? So b, you don't have the term here, so b should be 0. And c, delta square u over delta y square. So in this case, it should be delta square u over delta t square, but we don't have the term, so your c should be 0. So once we substitute, you get so the answer is 0. So let's try the last example here. So first of all, let's check the dependent variable. So in this case, the dependent variable is y. We are looking for y. So let's change all the dependent variables to be y. Then independent variable, you have x and t. So you have x and t here. So first of all, for the a, you need to find the d squared y over dx squared. So in this case, it will be y. So let's move this to the left hand side. It becomes negative. So for this term, it will be this delta square y over delta t square, which is this term. So this is your c. So we couldn't find this term, so therefore your b is 0. So when you substitute inside, you get 0 minus 1, and your c is negative. So negative become positive, you get 4 over c squared, which is greater than 0. So this is hyperbolic case. So for these 3 cases, there are important characteristics. For example, elliptic PDE is used to solve a problem that has this kind of behavior, time invariant, or in other words, we can call it as steady state. For parabolic, it solves the problem with time variant and non-oscillating. And last case, is time variant at the same time oscillating. So what are these? So for the first case, let's say you hot the plate, in different temperature. By doing this, let's say over the time, when you wait the time, let's say for 1 day, okay, you should be observed that the temperature distribution within this plate is constant, right? It doesn't change anymore. So when it's constant or doesn't change anymore, we call this as the steady state temperature. So at this time being, the temperature distribution on this plate is invariant, means doesn't change with time anymore. So from this equation itself, you can see that you are trying to solve the t in the function of x, y. So in this case, your t is the temperature distribution, and your x is the dimension in x direction and y direction. So if from the solution, if you get t 5, 6 equal to 10, so what does it mean? It means that at x equal to 5, let's say here is your x, and here is your y, which is 6. So at this point, your temperature here is 10 degrees Celsius. So actually you are solving a function for t that can describe all the temperature distribution within this plate. So if you remove the delta squared t over delta y squared, you will find that this is also elliptic case where you reduce to 1D problem. Okay, so in this case you want to find the temperature distribution for x direction only. So let's say this is the x direction. From this function you can tell what are the temperature change from this point to this point, right? So for the whole group. So of course you can add, okay, let's say you have add another term which is a z direction. So in this case we are dealing with 3 dimensions. So you are going to find the temperature distribution in x, y and z direction. So let's say you have a box here and you heat the box, let's say at the top 100 degrees Celsius, and you cool the bottom at 0 degrees Celsius. So you want to know what is the temperature distribution change for the whole body. So by solving this PDE, okay, you are able to know the answer. So beside the temperature distribution, we can also use the same PDE, okay, to find the flow, okay, water flow. So let's say you have a dam. So the water flow pattern and velocity, okay, is a steady state in this case. So we can use, okay. So for the elliptic PDE, it can be applied to find the temperature distribution of the heater plate. It can be also used to find the water flow velocity, okay, within the dam. So you can see that over the time, the flow of the water, okay, will be constant and steady state. So we can use to find it. Lastly, okay, you can be also find the electric field near the conductor, where you can see the magnetic field and electric field here is constant and steady state. So this can be solved by using the elliptic PDE. And don't forget, the keyword for this case is time invariant, means it doesn't change with respect to time. So this is the behavior for the solution. For example, the temperature that you found from here, the velocity, okay, that you found from here, and the electric field that you found from here is constant over time. For the case 2, in this case, we have the heat conduction equation as well, but instead of having 0 on the left hand side, you have some additional term, delta T over delta T. So T is the time, X is the dimension, let's say the capital T is the temperature. So you are looking for the temperature change over the X dimension and also over the time. So what does this mean? So since you only have x dimension, it will be one dimension problem. So let's say in this direction is x dimension. So imagine that you hit the bar here, okay, on the corner, and in the other end you cool it. So we expect some temperature change over the time. Imagine that initially the temperature, okay, the temperature should be capital, is equal to, let's say, 0 degrees Celsius. Okay, so imagine the temperature here, let's say it should be 0 degrees Celsius here. And you hit the thing at the corner here to be 100. And at the corner here to be 10 degrees Celsius, cold, for example. So at time equal to 0, at the moment you hit the thing, you should expect that, okay, the temperature here, it should be 100 degrees Celsius, the temperature that you supply, the heat, okay, and the cooling load, 10 degrees Celsius that you supply here. So at time equal to 0, you should expect this from happen. Okay, so here is approximate to 0 degrees Celsius. So over the time it will change. Okay, it might be like this as well. So this is just some approximation, right? Approximation. So in this case, it's like most of the bar is still within 0 degrees Celsius. At the time t is equal to 0, it should be like this. So when you supply the heat and cooling load, okay, over the time it will increasing the temperature because it is the temperature is hot here, and it will transfer and increase the temperature at the middle as well. So at time equal to 1, 2, 3 and so on, the temperature keep increasing until it reaches the steady state. So if this is the case, so over the time, okay, t equal to 3, 4, 5, 6, you don't expect the thing to be like this, right? So because your maximum temperature is only 100, okay, you expect something below the 100, okay? So this is not the correct answer. So you should expect the temperature will remain at one point, for example like this, and constant there. So at this point it's called the steady state, and there is no change in terms of the temperature over time. So actually what you solve here, so t x t is something time variant, which means that it changes with time, and you can see the solution is without oscillating. And from this result, okay, as the time, okay, proceed for a long period, and you will find that the temperature will remain, and this will change into steady state. So this means that as the delta t over delta t here, okay, when the t is a high, approximate infinity, then this will be equal to 0. So this will change to the first case, which is less than 0, elliptic problem. So it's so that in parabolic problem, when you solve it, you're able to obtain the transient solution where the temperature keep increasing, as well as the steady state solution. For the last case, let's look at this wave equation. So you are going to solve the y in terms of x and t. So it means that y, okay, in this direction is the vibration. So x is the dimension here over the time. So by obtaining this function, then you can tell, for example, like at time equal to 0, okay, so at x equal to 5 perhaps, so the vibration is here, x equal to 15 for example, your vibration y is here, okay, and you can predict for any time, let's say at time equal to 10 seconds, after 10 seconds, you might get some result like this. Okay, so x is the location in x dimension here, and it predicts the change over the time. So when we solve the hyperbolic PDE, we expect the solution to be time variant and also oscillating. So this can be applied to other applications, such as the motion of the fluid wave, as well as the transmission of sound and electrical signals.